Hey guys, welcome back. So, the next topic is probably if you're ever going to go into analytical chemistry, um, this is probably pretty much your bread and butter. We're going to be talking about titration, and more specifically in the context of acid base reactions. Now, let me just quickly describe what titration is, and then we'll sort of describe what it's used for, and then sort of go into how you would process data. And as much as I would love to show you how it's done, I don't have the equipment for a school lab. I'm basically at my house, and I don't have the equipment you would need. But I'm sure someone has a video on it. So without further ado, now the formal definition of titration is a method of qualitative analysis based on the reaction of two chemicals that react according to a known stoichiometric ratio. Basically, basically it's used to determine how much of something there is in a solution, and that's really useful. Now, provided you know what's in there, you can use it to do all sorts of useful things. Like, for example, um, you can only have a certain concentration of lead in drinking water before it becomes toxic to people. So you can, titrate for lead in the drinking water. Now, mind you, the concentrations that you would find in the water are very, 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 very small. However, it is important to check for that sort of thing, or when we go into study redox chemistry, there's a quantity known as biochemical oxygen demand, and it determines the sort of purity of water, and you can use it to measure the health of an aquatic ecosystem. So these things have uses in the real world that are not just chemistry, um, mainly in health and safety and ecology and stuff like that. Now, Um, basically, what it actually amounts to is you're just dumping two solutions, and you're dumping them such that you do it very carefully, so you know how much of one solution you dunked in the other, and you know the concentration of that solution, so you can get how many moles of it reacted, and you can use your mole ratios to determine how much of that stuff is in there. Now, let's go through a bit of vocabulary here. So the titrant is the solution. So this is sort of the apparatus of a titration. So this is what we call a burette. It has a stop clock with a flask with a magnetic stirring bar and stirrer. And this is the solution of analyte. That's the solution that you're titrating it with. This is what we call the stopcock, burette clamp, and here you can measure the level of titrant. So the titrant is the solution in the burette. So it's the thing you're dumping in, and you're supposed to know everything about it. The analyte is the substance being analyzed using the titration. So generally, the analyte is there's something that you don't know about it. So it's HCl of unknown concentration, and you titrate it with 0.1 molar NaOH. The titrant is slowly added into the analyte solution until the reaction is just complete. Now, how do we know when it's just complete? We can um, generally, what this amounts to is you generally have a color change. So, in the case of an acid base titration, since you know it's neutralized when it's at pH 7, which is defined to be neutral. Now, this isn't always the case, but um, for the standard levels, this is the case. So, you could add an indicator that changes color at pH 7. So, say it goes from yellow to blue or something, and you know it's done when the solution turns blue. Or for redox chemistry, you generally do something called idiometric titration. And the reason that is because iodine is when you mix it with starch, it turns into a very dark blue color, and when that color disappears, that indicates that the reaction is done since there's no iodine left. So that's generally how you determine when the reaction is done, and when you reach that point, it's called the equivalence point, which formally is defined as the point of the titration when there's enough titrant added to the analyte such that the reacting chemicals are in the correct ratio and there's no excess reagent. And the end point is the experimentally determined equivalence point, which is always more than the true equivalence point, at least by some fraction of a drop. Now, the end point is actually what you determine in the lab using, the pH color, using the indicator, the change of color of the indicator, or a disappearance in color, but generally you do it through a change in color. So at the equivalence point, at least for this titration, this type of titration here, the following statement is true. The moles of this equals the moles of that added. All right. So now that you actually have an idea of how this sort of works, let's process some data. Now, a common I should have probably been a bit more prepared, but a common sort of there's all sorts of variations on this method of titration. You can do back titration, or a back titration is a common one, which is basically you add something, you dissolve something in a solution that you know the concentration of, and you dissolve something that you don't know into it, and then you titrate that solution with the water, or you titrate a portion of it with the water. It's really simple at its core, but you can get very complicated very easily. I might do a video worksheet with a more complicated titration problem, but let's do a simple one here. Let's see how much time I have. Yeah, let's do a simple sort of titration problem. Actually, you know what? Let's do a slightly harder titration problem. So let me find something here. Now, I myself don't actually, I'm just going on Google here. I can't find it. But there was a common lab that you'll be doing is dissolving eggshells in hydrochloric acid and then titrating it with base to determine how much calcium carbonate was in the eggshell. But since I can't find anything, here, let's consider question 4 here. Pause the video right now if you want to try it, and I'll be going to the solution in 3, 2, 1. Alright, so I assume you're back. Firstly, a general good rule of thumb is to write out a chemical reaction for this stuff. So you generally you have HCl plus KOH, KCl plus H2O. Generally, that's always a good starting point to add sort of what sort of reaction are you doing. Now, using our little chart here, so before, after, and so this is an impure sample of potassium hydroxide, and we want to know how much there was in there. What's the purity of it? So what we do know is that, so we know that, so we want to know how much of this is actually KOH. So what we do know is that we know, so let's put an unknown here. So after the reaction there would be none. And then, so what we do know is that the initial reading from the burette was 2.87 mil VI, and VF was the final volume. Here, let me do this. Let me sort of do these calculations, these sort of volume calculations off to the side. So what we do know is that VI is 2.87 milliliters, and VF equals 31.67 milliliters, and we know that the concentration of HCl was about 1 molar, right? So using these three things, what we can do is we can calculate how much HCl was in there. Now, if we had an initial volume of that and a final volume of that, what's the difference in volume is more or less what we should be asking ourselves. Which, let me pull out a calculator here to sort of do the math. Excuse me. So what we can do is we know the volume delivered is VF minus VI, which when I do that in my calculator, so 31.67 subtract 2.87, I get a volume of 28.8 mils. So I know that there was 28.8 milliliters, and I know that since I know the concentration, let me resize this. Let me just resize everything here. I know that there was a mole for every 1 liter, which is the same as 1,000 milliliters. So if I divide this by 1,000, I get that there was, which equals 0.028 0.288 moles of hydrochloric acid, and since we know that this is a 1-to-1 mole ratio, there was 0.0288 moles of potassium hydroxide in the solution, right? Now, we want to determine we want to determine the purity of the sample. And we know the mass of the sample, but we don't know the mass of potassium hydroxide within the sample. Now, thankfully, since we know how many moles are in the potassium hydroxide sample, we can use the molar mass to convert here. So if I go to another page, so 0.0288 mole, 1 mole, and then the molar mass of potassium hydroxide. Just give me a moment here. What's the molar mass of potassium? I should have these things more prepped, but potassium has the molar mass of 39.0983 plus so the molar mass is 56.11 grams, so times that gives me 1.62 grams, and since we know that the sample mass was 1.76 grams, that was given in the question, we get that the sample had a purity of about 92%. It was, I don't want to be an ass about it, it was 91.8%. So the sample had a purity of 91.8%. And that's, and that's sort of the basics of titration. That's sort of what we can do in the lab. We can determine the purity of that sample. Now, there are obviously much more complicated methods of titration that you may need to do, some of which we'll cover in future videos, but that's sort of, I hope that gives you sort of a view for what the basics are like. Thank you for watching. Don't forget to like and subscribe.